Okay, so with that we come to the topic of parameter estimation. So first, what we will do is that we will go through the basics of parameter estimation. Uh, Now, what essentially is parameter estimation? What does one mean by parameter estimation? Or, for example, the other question might be, how does one measure a parameter? You see, any measurement involves measuring a change. For example, let's say I need to measure the mass of a cricket ball. Uh, Now, this measurement, how would I measure it? Well, I'll take a spring, which is basically my probe. And what I'll do is I'll just attach the ball to the end of the spring, and I'm going to measure the extension of the spring. And this is the way, after measuring the extension of the spring from its initial position, uh, of course, this particular experiment, I had a probe, I measured the change in that probe, and then I made measurement, extension of the spring from its initial position, and of course I repeat this measurement many times, m1, m2, mn, and based upon measurement statistics I get an estimate of the parameter x, which was in my case the mass. So let me label these guys as L1, L2, L3, because this is what my actual data look like. L stands for length of the spring, and that estimate gives me an estimate of the mass m of the object. So how does one use quantum mechanics? How does one use quantum states for parameter estimation? Well, the idea is simple. One uses the way we used a spring. We are going to use quantum states as a probe. So what I'll do is that I have an initial state. I'll have a parameter which is going to cause the change in state. And I'll get some sort of a state after the application of parameter. We'll come to that. Let me call it the changed state. And then I am going to perform a series of measurements, M1, M2, so on, Mn. And I'm going to, the state has changed as a function of the parameter which I needed to measure, just the way the spring elongated as a function of the mass m which I needed to measure. And based upon the statistics build, I'm going to invert these statistics and I'm going to measure the parameter. So how do we go about it? Well, the idea is that we can start with an example. So consider that I need you to measure a frequency, omega. Or I can say I need to measure a parameter which I embed as a frequency, omega, which I embedded in a Hamiltonian. This is my Hamiltonian, sigma z half h bar omega, and usually I'm going to use interchangeably h bar to be 1, the Planck's constant. So this was my parameter. What do I take it as my probe? Let me draw the block sphere. Remember we did this, the block sphere in the class, months back. So this is my block sphere. This is my zero state, or I also call it the spin up state. This was the one state or spin down state. I had the, so plus x minus x plus y minus y. This is how my block sphere look like, and what I'll do is that I'll start with my state. What I'm going to do is that let me start with this state, which I also known as the plus x state. This is over here. So what do? I act on the state with my Hamiltonian. And how would I get this state? Well, I'll get this state with some sort of a rotation of my initial state. I rotate it towards about the y-axis. I rotate this pi by 2, a pi by 2 pulse. So I have this initial state. This is state 1. A pi by 2 rotation about the y-axis. I call this guy as y, means this is the rotation about the y-axis. A pi by 2 pulse, that's going to give me an equal superposition of plus up state and down state. Well, I'm using the same symbol, so this is the same state as or plus 1, which is this particular state. And then what I'm going to do is that I'm going to operate it with my Hamiltonian. Mind you, my Hamiltonian has the parameter embedded in it. So what does this action of this guy, this Hamiltonian, which causes a unitary evolution. So this is a unitary evolution by a time t by this Hamiltonian, for a time t by this Hamiltonian. What is going to happen is that the eigenstates of sigma z, notice my Hamiltonian was, this was my unitary operator where my Hamiltonian was given by half h bar omega sigma z. So I just get a relative phase shift, phase difference, the eigenstates plus and minus are going to pick up this phases due to the unitary evolution. Now notice I have the information about the parameter I was supposed to measure, omega. I have it in the state. So what's happening is that my state over here, due to the action of the Hamiltonian, let me call it state 2, which was the step 2 over here. After this rotation by the, what's going to happen is that my state rotates about the z-axis and it's going to pick up a, this is on the equatorial plane. This is my state 3, which is this guy. And this rotation is going to be proportional to omega. So I already have the information about the parameter I was supposed to measure embedded in the state. Now all I need to do is to find a way to extract this information. So for what I do, for that I do is that I give it another rotation about the y-axis by pi by 2 so that it flips over. So what do I get? After that, you can just try it offline, but the answer I get is minus iota sine omega t by 2 plus, or up arrow, plus cosine omega t by 2 downstate. So this was step 4, where I'm again going to flip it back up. So what's essentially happening? From the equatorial plane, this state again lands up somewhere here. This is my 4th step. This is my 4th stage. I have converted the information which was embedded in the phases now as an information that is going to be in the amplitude. So now if I measure the spin in the up or the down direction, I'll have different probabilities. Over here at stage 3, if I had measured in the up and down direction, I would have had exactly the same probabilities given by half, because see, this is a complex number. Nothing really happens because of this phase as far as the probability amplitude is concerned. So I had to convert this phase information into an amplitude information for parameter estimation. So in other words, after my stage 4, what really is happening is, I'll write it down again. This was what I had. Here I had the information about the parameter I'm supposed to measure as phases, and I again give it a pi pulse rotation, and I get this guy. Now what do? I measure the probabilities of the particle being in the up state or the down state using the Bond's rule, and I get my statistics. Similarly, for the probability of finding this state in the downspin direction, over here. So fantastic. Now I have different statistics depending upon what my measurement is, and the probability which is a measurable in my experiment is a function of omega over here. And I do this experiment many times, build up my statistics to get some information about omega. So we are going to, so this was an example of how a quantum state is being used to measure a parameter. So this is an example of quantum metrology. Now the question arises that is quantum metrology superior to classical metrology? By classical metrology, I means that I am not using the quantum nature of particles or quantum nature of light to measure things. And if it is superior, in what way? So as you can guess, certainly it's going to be a statistical argument, because both in quantum limited metrology, quantum metrology, and classical metrology, I'm going to measure many times, build up the statistics, and invert. So, which, to appreciate that leads us to our topic, the next topic. In order to appreciate the advantages of quantum limited metrology, I come to the field of statistics of parameter estimation.